So welcome everybody. This is Marco Rossi, and that's my presentation, Hit-reco, ProtoDUNE Denoising with Deep Learning Models. Let me first present you DUNE, which stands for Deep Underground Neutrino Experiment. The DUNE Experiment is based in the US, and its main goal is to have a deeper understanding of neutrino physics. In particular, we have two facilities. One is at Fermilab in Chicago, where the most intense neutrino beam is produced. And these neutrinos travels all the way until they reach a far detector underground in the Sanford Underground Research Facility in South Dakota. At CERN in Geneva, we have ProtoDUNE, which is a prototype of the DUNE spark detector in scale 1 to 20, where its main goal is to test and validate DUNE's technologies for the forthcoming experiment in the US. In the picture here, you see the detectors box. This detector is called LATTPC, which stands for Liquid Argon Time Projection Chamber. This is a big box filled with liquid argon, and it works as following. A particle, as you can see here, a particle like a neutrino comes within the detector and scatters with the nucleus of argon that are inside. And since electromagnetic field is established inside the detector, the produced particles after the interaction are drifted rightwards in the case of negative charged particles like electrons. These electrons are collected by these planes that are a set of wires that are called anode planes. And this set of wires collect the induced current by these drifting electrons. We have then these two kinds of raw data that are data coming out from the detector. We have a one-dimensional view that is the current induced by these electrons on a single wire and calculated by the detector at different time steps. So we have a one-dimensional array. On the other hand, we could have a two-dimensional view of this raw data, that is the whole number of wires inside each plane against the time on the other axis. So we prefer using in our models the raw data in the two-dimensional view, but sometimes it's useful also to see what's happening in the one-dimensional one. Here on the x-axis we have the time, as I said, and on the y-axis we have the number of the wire. In the one-dimensional view, we select a single stripe, horizontal stripe of this data. The traditional workflow of line data processing works like these steps. We have initially we have a simulation or detector that simulate or measure the incoming particles and produce this raw data that I just explained before. And after that, we have the reconstruction step, that is kind of a feature extraction. We have split this reconstruction in different steps, the denoising and it finding, which means that we have to see if each pixel contains or not contains signal inside it. And the final parts of this reconstruction step is given by particle identification and event labeling. These reconstruction products are then gathered together to form a theoretical model inside an analysis step. This is made to have a final insight of the physics of the neutrinos. The goal of my research is to replace the reconstruction traditional algorithms with deep learning model. And in this presentation, I'm going to focus just on the first two parts here, the denoising and the region of interest selection, that is equivalent of it finding. Again, let me present the kind of data we have to deal with. We have these kind of features that we have noisy waveforms, as you can see here in the one-dimensional view. And also you can see from this picture that the images have sparse signals inside them, and also they are really big. They have 960 per 6,000 pixels each, so really big images. In order to deal with these two features that could constitute difficulty in the models, we employ graph convolutional neural networks in order to deal with sparsity, and with the size of the images, we use a data parallel approach, meaning that we are cropping the images and feed the crops to our models. Here, I've spoken about crops. Here we have a sample of noisy images on the left and the corresponding target images, denoised, or well, the labels on the right, in a two-dimensional view. In this slide, instead, we have a one-dimensional view. As you can see, the target waveform is cleaner than the noisy one, of course, that is used as an input. We built a dataset containing 10 simulated events. Each of these events have 6 planes where the data are collected that simulates the detector planes. And all of these 10 events are split into train, test, and validation set, as in this pie chart shown here. The raw data size in memory is takes 7 gigabytes for both inputs and labels. And as I said previously, planes in the train set are cropped to fit in memory and to be fed to our models. So we randomly sampled 24,000 crops, 32 by 32, while test and validation set contains 6 planes each, which are 1 event for test and 1 event for validation set. Each planes is 960 times 6,000 pixels each. Let me present now the proposed model we are going to use. This is the graph convolutional neural network layer given by this paper referenced here. The graph convolutional layer is an average of 2 operations. The convolutional of a 3 by 3 filter that takes care of the relationship between the pixel in question and the correlation with the local pixels. While the non-log aggregator builds inside a graph, a K9 graph with K equal to 8, and exploits long distance correlation between pixels. In particular, we have that for a red pixel, its receptive field is comprised of the closest, the 8 closest pixels in feature space, where the distance in feature space is computed as a Euclidean distance. Difficulty, the caveat to have in mind when we employ this kind of layer is complexity. Namely, the complexity is of order n square, where n is the number of pixels inside the images. So if we choose to have square crops, the complexity is quadratic against the sides of the edge of the crop. Our interest in models is twofold. First, we want to perform an ROI, namely a region of interest finding selection, which answer the question, does the pixel contain a charge deposition? Secondly, I'll show that we will also employ our models for a denoising task. But as for this ROI, the output of the model is 1 when there's actual charge, so there's signal inside a pixel, and 0 when the signal there is not present. In these plots, you can see the output of a trained ROI block and the target. For the color coding, yellow means 1, so signal inside, and violet means no signal. The output is given by a softmax layer, so we have to cut with a threshold this kind of output in order to have the final output that I show you after. The technical features of this ROI block. Well, this ROI block takes as inputs the noisy crops and outputs the hits, like this one. It's comprised of several stacked layers. First, we have the several convolutions, 7 by 7, with filters of these sites, and then some graph convolutional. I'd like to anticipate here that we are going to use two kind of models. One kind is this actual graph convolutional neural network, and the other one is a convolutional neural network. I called convolutional neural network the same architecture, but with layers like this one, so the graph convolutional ones, replaced by usual convolutions. This is to have some benchmark, some comparison between the outputs and the performances. The dimension of the ROI block is of 10 to the 5th trainable parameters, and we train this net with binary cross-entropy loss functions and the Adam optimizer. As I anticipated before, this is a part of a two-folded aim. The second task we want to perform is the denoising. Denoising is carried out by this bigger network. As before, it takes as inputs the noisy crops and outputs a denoised crop. As you can see here, we have an early stage of processing that is comprised of some pre-processing blocks and an ROI, so a full trained ROI presented before, which output is concatenated with the other and then passed by some filters. Again, I'm going to speak of GCNN with this kind of architecture and CNNs when denoising, where the green layers are replaced by convolutional yellow ones. In this plot, you can see an example of output of a trained model, denoising model, and its correspondent target. So visually, they are quite indistinguishable. As technical feature, again, data inputs are crops 32 by 32, and as you can see by the number of trainable parameters, this model is 10 times bigger than the one before, and is 10 to the 6th parameters. We trained the models with a custom loss function that is comprised of this sum of 1 minus structural similarity plus mean square error. Mean square error is defined in the usual way, while structural similarity is a custom perceptual loss that means that gives higher scores for indistinguishable crops. So the more the crops are similar in a perceptual way, the more the structural similarity value computed by this formula here is high. The structural similarity in particular is bounded between -1 and 1. Then taking 1 minus SSMI gives you a positive definite number, and where 0 is the perfect score, as we would like to have for loss functions. Again, we train with the Adam optimizer. Our working environment is given by an IBM Power 8 CPU, and we used 4 NVIDIA Tesla P100 16 gigabytes each GPUs. We coded everything in PyTorch. And now let me present some training scores, starting from the matrix, here you have two plots. The one on the left is for the training loss, the binary cross entropy for the region of interest selection, and as you can see, the CNN behavior is smoother. While on the other hand, we have on the right plot the validation matrices. But as you can see here, the best score on validation set is given by the GCNN on epoch 15. The timings for training the region of interest selection are given by these plots. We have the absolute timing and the ratio for training, either for graph convolutional neural network and convolutional neural network. The ratio between the two is 2.5. So CNN is 2.5 faster than GCNN, but this can be expected because CNN is optimized by PyTorch programmers, and while GCNN is just a custom layer. On validation, we have a factor of 7 of speed up for the CNN. What about the denoising training? So we train before the ROI block, then use a pre-trained ROI block to be loaded into the denoising block, and then training everything together with the custom loss function. As you can see here, the GCNN and CNN are quite well behaved on training. But the GCNN validation loss is almost always below the CNN ones. We present here several metrics for validation on the validation set. Just have a focus on the PSNR, which is the peak signal to noise ratio. It's kind of a logarithmic scale for the mean square error, and higher scores here are better. So as you can see here, the blue line is almost always above the orange one. As again, for the timings of the denoising, we have a factor of 4 for the GCNN to be slower than the CNN on training, and a factor of 5.6 on validation. So this is comparable to the previous results. Now, we decided to benchmark the regions of interest selection trained on our dataset against a basic Kenny filter. This Kenny filter is a basic edge detection tool, which is known in computer vision, and answered the question, does the pixel belong to an edge or not? It's comprised of a convolution and a thresholding method to label the pixels. Just to mention, we have in test set 6 planes, then an order of 34 millions of pixels, but these pixels are really unbalanced, meaning that the ratio between hits and non-hits is 1.9%. So we choose a figure of merit like the sensitivity because we wanted to wash out the whole empty space in the images. The plot shows here the final evaluation for the sensitivity for each of the 3 algorithms. The Kenny one is not suited. I would say that this is not suited for this purpose to process our dataset. But we achieve a best peak signal peak sensitivity of 0.85 with the CNN network. Here we present the scores histogram. The green lines are histograms for pixel without any hit inside. So in principle, this a best classifier would have classified these pixels as zeros, while the red curves are its pixels. So pixels that would have been attached a score of 1. The solid line is regards the CNN, while the dashed one the GCNN. as you can see, the GCNN is more separated, is less separated, sorry, than the CNN ones. So as in the right, as the right plot points out, the CNN achieve a better performance also in receiving operating characteristic curve with the area under curve parameter that is higher for the CNN of 0.996. Here we present the results for the region of interest in the form of the two-dimensional plane. We have the target in the first plane, while the second and third is the CNN and GCNN. We see that neural networks perform good in the region of interest selection, but isolated pixels are difficult to be matched by these algorithms, while they are targeting the clustered ones, the clustered pixels, so tracks like these in a really good way. On the other hand, Kenny performs poorly on this data set and focuses just on these cluster tracks, but this performance is not high enough to compete with the other neural networks. As for the denoising benchmark, we benchmark our denoising model, so the full big model, against Wiener filter algorithms. These are just naive convolution with Gaussian filters. We employ three different kind of filters, one 3x3, one 5x5, and one 7x7. We collected here the scores in terms of peak signal to noise ratio on the left and structural similarity values on the right on the test data set. And we see that the GCNN achieved the best performances with the peak signal to noise ratio of 70.5. Now I'd like to present here a result for the denoising and to show here what's going on better. I plot here the waveforms in a one-dimensional view. So on the x-axis we have the time ticks, and on the y-axis we have the ADC values, namely the current values induced by the electrons. You can see that on the top plot we have a wire with some hits inside, so a wire that contains actual signal, and this is given by the spikes here, while on the lower plot we have a wire without any signal. So on the upper part you can see the high end of this peak is given by this gray line, and it represents the target, while the CNN and GCNN are respectively the orange and violet curves. They reconstruct perfectly the position, so the position meaning left or right, and the shape of the peaks, but they struggle a bit about the height of this peak. However, the Wiener filters, so the benchmark we made, are not able to reconstruct the position of the target spikes and show displaced peaks, as you can see here in these greens, by these green lines. On the other hand, in the lower plot, the target is hidden behind these lines, and since this is a wire without any signal inside, the target would be a constant function at 0. And you can see that just the best performing algorithm is the Wiener ones, because these Wiener are closest to 0, while the neural networks are slightly biased from below, and maybe this is due to the fact that neural network are somehow reminiscent of the noisy inputs, so they struggle to remove the noise from the empty space. In summary, we presented the denoising and region of interest selection models for ProtoDUNE. we employed simulation data, so Monte Carlo data, and we benchmarked our CNN and graph neural network models against basic algorithms, the Kenny and the Wiener filters. And we decided in light of the results, we decided the best model is a CNN region of interest selection and a graph convolutional neural network denoiser. For future work, we commit to make a hyperparameter tuning to improve performances for the models. Thank you very much for attending this talk, and let me know if there are any questions.